All right, let's take a look at an example of equilibrium of rigid bodies in two dimensions. This first example, what we have is some kind of pickup truck with two boxes or containers, C and D. We're given that the weight of the truck is 13,734 newtons. You can see that's right at this G value for center of gravity. Two crates both weigh 3,434 newtons. What we're going to find is the reaction at each front and rear wheel. Each meaning there are two wheels in the front, two wheels in the back, so we're going to have to figure that into this whole thing. And so, like we said last time, a strategy that we want to follow is the first step would be to in essence, draw your free body diagram. Well, this one, I'm going to draw right on the picture. The only reactions I'd have is at A, I'm going to put 2 because there are two wheels times the reaction at A, and the same thing at B, 2 reaction at B. And those are the only two unknowns I have. So after I draw my free body diagram, I said the next step is to sum the moments about a point that'll make at least one of those unknowns go away. So I could either do sum of the moments about A or B, and it doesn't know if I don't know if it makes much difference. I chose to start off by saying sum of the moments about B is equal to 0, with our same counterclockwise being positive. And here it's just a matter of I'm going to work from left to right. I'm going to start off with the weight of the truck, 13,734 newtons. The distance away is this 1.2 meters, and that is a positive moment because it creates a counterclockwise moment about B. Same idea with the crate D. So crate D, I'm going to say plus 34. Its distance away would be that 0.85 plus 1.82, which would be 2.05. And it's also positive counterclockwise. And then I have the reaction at the other wheel. So now that is going to be a negative because this reaction is creating a clockwise moment about point B. So I have minus 2 for both wheels, the reaction at A. That distance away would be another, 0.95, giving me like 3 away. And then I have to get the other crate on there about point B. This is also creating a counterclockwise or positive moment. And its distance away would be this 3.75. Set the whole thing equal to 0. I can solve my reaction to A, and looking at my notes, I got 6,067 newtons. Now that I have one, I can move on to sum of the forces in the y direction equals 0. My other equation, sum of the forces in the x, doesn't do us any good here. I could do sum of the moments about point A to find the reaction at B, but I think it's easier just to move on to sum of the forces in the y. Most people like that. There's no multiplying together. So now we have, I'm going to start off with my unknown. I have two of these reactions at B, and then reactions at A is pointing up, 6067, and then I have my forces going down. So I have minus 34 for one crate, minus 34 for the other crate, minus 13,734 for the weight of the truck. Set the whole thing equal to 0, and I end up with a reaction at B of 4,234 newtons. So if I were designing a wheel bearing or tires and wanted to know the weight on each tire or something like that, I could find it from this using statics, and I find out that on each tire, each wheel, I have 6,067 at A and 4,234 at B. Let's take a look at another example. This example, I have an elbow looking shape. I'm supporting two 240 Newton forces, and there's a pin connection at C. I can see that, and then there's a rope going from D to this pin connection at E, holding the whole thing in place. So we're looking to find the tension in the cable and also the reaction at point C. If I were to draw the free body diagram, I would once again draw it right on there. Looking at this A, B, C, D is like this elbow is really my object. So from that, I know I have a tension in the cable, that's what I'm looking for, between D and E. And at C, now that's a pinned connection, so I could have a reaction at C in the Y direction and a reaction at C in the X. I don't know where to draw that. I'm going to put it there, I guess, CX. Hopefully you can see that. And after I have my free body diagram, now I want to pick a point to sum the moments about that'll make many unknowns go away. And in this case, what I would choose to do is I would sum the moments about C, because that makes both CX and CY go away. And so working my way around, now I have that tension's at an angle. So the way I'm going to deal with that is I'm going to resolve that tension into components. I can resolve it into a tension in the x direction and a tension in the y direction. Now tension in the y goes right through C, so there is no moment. All I really care about is tension in the x, right? So I'd have tension in the x direction times the lever arm, and this is positive, meaning it's going this way about point C. And its lever arm would be that 0.18, or that y distance. Then I have those two 240 Newton forces. The first one is 0.4 away. Now these are creating clockwise or negative moments about point C, minus my other force and its distance 0.8. Set the whole thing equal to 0. I do have to figure out what that x component for t would be, and the way I'm doing that, like we've done before, is I'd find the hypotenuse for this cable DE by saying it's just equal to the square root of, let's see, what is it, 0.24 squared plus 0.18 squared, and that gives me, what, 0.3. So for the horizontal component, it's just the distance in the horizontal direction, that 0.24, divided by the hypotenuse, 0.3. We've done enough of those. Hopefully that's not too bad. That's my TX. The lever arm is 0.18. Don't forget that lever arm. Minus, and I'm basically just rewriting the whole thing. And maybe you would have done this in one step and not taken that extra time. But with that, I can solve for the tension, and I got a tension of 2,000 newtons. And after I have that tension, now I can move on to some of the forces in the x and the y direction. Let's start with the x direction first. The only reason I'm starting with x, I don't really have a reason. I guess it looks like there's just less to it, right? So I know I have a tension in the x direction, and it's actually pulling in that negative x direction the way I have it. So I'm going to put minus tx plus cx and set the whole thing equal to 0. Now we've already talked about Tx. We have the magnitude of T, which is 2000. The x component would be this 0.24 over 0.3 plus Cx is equal to 0. Solve for Cx, and I got Cx is 1600 newtons. I got positive, meaning it's pointing to the right. Last but not least, we can use some of the forces in the y direction equal 0. In the y direction, once again, that tension is pointing, it's in tension, so it's pointing down. The cable is pulling down. So I have a negative 2,000. And for the y component, I'm looking at my y distance of 0.18 over the hypotenuse of 0.3. And then I want to know what my cy is going up. Don't forget you have those two 240 external forces pushing down, set the whole thing equal to 0, and from there I can find cy is 1680 newtons. Now I prefer to actually leave it like this with the cx and cy. If you're looking at other resources or textbook or something like that, they usually put those cx and cy into a single vector. So that last step, if you wanted to, I'm never going to require you to do this, would be 1600 in the x going that way, 1680 in the y. So we know if we wanted to just find a single value of c, we could just square root those and get something like 2320 newtons. I suppose it would be important if you were designing the cable and you wanted to know the total force in the cable. Actually, this is for the pin at C, isn't it? Well, it's still the same idea. If you want to make sure you weren't going to shear off the pin, you might want to know something like that. And if you were doing it this way, you'd also want an angle in there, so that theta could be found by taking the inverse tan of the opposite over the adjacent, which is 46.4 degrees, and then that's measured up positively from the x-axis. So that's an alternative. I personally just leave it as cx and cy, but whatever rocks your boat. So I hope those examples help drive home the idea of static equilibrium in 2D with rigid bodies. Let me know if you have any questions or comments. Thanks.